So this is a question which is asked by one of the student. Uh, so here we have a uniformly wound solenoidal coil of self-inductance some L and resistance R, which is broken into two identical coils. So let me draw that coil here first. So let's say here we had some coil which had a self-inductance L, resistance R. When we break this coil into two parts from the middle, so one coil this, another coil like this. So because we know that the inductance L is given by mu naught A, area of cross section, n square, n is the number of turns per unit length, into L, L is the length. Because we know that the inductance is proportional to L, so keeping the other things same, if we reduce the length to half, L by 2, then the inductance will also become L by 2. Same is the case with resistance. Resistance is rho L by A. So if this A is different from the other A, this A is the area of cross section of solenoid, and this area is the area of cross section of the wire of which solenoid is made up of. Okay, so in case of resistance, we are talking about the area of cross section of this wire itself, this tiny area of cross section that you will see, whereas in case of a solenoid area, we are talking about this area. This is the diameter. But anyways, so is the length also. In case of a solenoid, the length sorry, in case of a solid, the length is this L, whereas in case of a resistance, the length that we will be considering is the length of the wire. So it's like when you straighten out the solenoid, stretch the solenoid and make it straight, then what is the length that you will achieve? That length should be used to calculate the resistance of the solenoid. So this length and areas for the calculation of resistance of the solenoid is different from the area and length that we are using to calculate the inductance of the solenoid. But anyways, when we cut the solenoid into two halves, then the resistance also becomes half because of length becoming half, and inductance also becomes half because of length becoming half. Now when you keep these two in parallel and connect it to a battery, then definitely here we have an LR circuit. Now the thing is, here we are having two different LR circuit. One LR circuit like this, and the other LR circuit will be like this. The thing is that both these LR circuits are identical in nature, because in both the LR circuits the L is also same and R is also same. And so whatever current is here I1, the same current here will be there I2, and so the I net will always be 2 times of I1 or 2 times of I2. And so this, when I1 becomes, let's say, half of its maximum possible value during the growth of current, the I net will also become half of its maximum possible value, which means whatever is the time constant for I1, same is the time constant for I2, and same is the time constant with I net, because the time taken to reach to half of the upper maximum value, or half of the one third of the upper maximum value, or whatever, like so it is all same. So they will follow the same kind of trend. At the time when I1 becomes 30% of its max value, I net will also become 30% of its max value. So this I1 can be written as E by R, E raised 1 minus E raised to minus R T by L. And same is the case with I2 also. And I net is simply double of this. And so the time constant wise, which is, you can say, the coefficient of this E, I mean T by tau we write now. So E raised to minus T by tau. So this tau term will be same for I1, I2 and also I net. The only difference between I1 and I net is this the front part, which is the multiplication part, which is becoming twice in case of I net without changing the power of E. And since the power of E is same for I1 as well as I net, the time constant is same for I1 and I net, which is equal to uh, L by 2 divided by R by 2. So 2 2 also gets cancelled, so we get same L by R only.